But anyway, welcome back everyone to the night session of Wombat 2021 on Monday night. We have 3 speakers today. We'll get started soon. I have one housekeeping announcement that I have to make, that the program will be updated with minor changes. So the program is on the website, the PDF document on the website, that will be updated with minor changes, and it already has been since I sent out the email. So I encourage you to check that out periodically. Okay, so tonight we have 3 speakers, as I mentioned. The first one is Nikolai Osmolovskii from the Systems Research Institute at the Polish Academy of Sciences, who will be speaking about on the strong subregularity of the optimality mapping in mathematical programming and calculus of variations. So on that note, I'll hand it over to Nikolai.
Thank you very much, and thank you for inviting me to this conference. This is a joint talk together with Vladimir Velov, and our talk is dedicated to the memory of Asen Donchev. Here's the content, and I will start with literature. There is a lot of different papers. Here I would like to pay attention to this paper by Cibulka, Donchev, and Kruger. We shall use finite dimensional results from this paper, and we shall use some notions. Further, I would like to show you, of course, we shall use some notions from this book by Donchev and Rockefeller. And also, I would like to mention the paper by Malanovsky, two-norm approach instability analysis, and so on. We shall also use two-norm approach. And my talk is based on our joint paper together with Vladimir Velov in the Journal of Mathematical Analysis and Applications. So, first, I would like to present the notion of strong metric subregularity. It will be a little bit different from the usual one. Let X and norm X be a Banach space in which one more norm with prime is defined such that norm with prime is less or equal than the basic norm. For example, and this is an important example, X is equal to L infinity, and the weaker norm is the norm of the space L2. Let L be a set-valued mapping to another normed space, Z, and we have the following definition. Let the mapping L, we say that mapping L has the property SMSr2 at the point S hat for Z hat, if Z hat belongs to the image L of S hat, and there exist neighborhoods of the point S hat and of the point Z hat, and a number kappa such that these relations imply this estimate. And I want to pay attention that here in the left-hand side we have a weaker norm. The distance between S and S hat is estimated in weaker norm. We shall use this definition for Z hat equal to 0. The only difference between SMSr2 and standard SMSr property is the presence of this second norm. We shall consider the following mathematical programming problem in the infinite dimensional spaces. Let X and Y be Banach spaces. consider this problem, MP, where all mappings are C1. And let X hat be admissible point, define the set of active indices E. E is the set of such indices so that Fi of X hat is equal to 0. Let us recall the definition of Mangasaryan-Framovitz constraint qualification, MFCQ. Assumption 1. The image of the space, the image of the G prime of X hat, this is Fréchet gradient, X is equal to Y. So this operator is surjective, and the gradients Fi prime at the point X hat for active indices are positively independent on the subspace Ker G prime of X hat. Recall that the functionals L1, Lk are positively independent on a subspace L if the conditions that the linear combination of these functionals is 0 on the subspace and all coefficients are non-negative, implies that all coefficients are 0. Theorem: if X hat is a local minimizer and assumption 1 holds, then there exist lambda and Y star such that we have these conditions. The above relations are known Karush-Kuhn-Tucker system, and the triple X hat, lambda, and Y star that satisfies these conditions is called Karush-Kuhn-Tucker point. We fix Karush-Kuhn-Tucker point X hat, lambda hat, and Y star hat. Now assume that in the Banach space X there is another weaker norm, norm prime, and we make the following two norm differentiability assumptions for the mappings phi, f, and g. First, we formulate this property for G. Assumption 2. There exists a neighborhood of the point X hat in the basic norm, such that the following conditions are fulfilled for all delta X, such that X hat plus delta X belongs to this neighborhood. First, the operator G is continuously Fréchet differentiable in this neighborhood in the basic norm, and the derivative G prime of X hat is continuous operator with respect to weaker norm. Moreover, the following representation holds true. Here, R of delta X is simply O small of delta X, but O small in this sense. We have here weaker norm. I would like from the very beginning to say that all these assumptions fulfilled for problems of calculus operations, for optimal control, it will be fulfilled automatically. Then there is a bilinear mapping Q from x to x times x to y, such that we have this. R bar is O small of delta X, again in this sense. And Q is estimated from above by X1 prime, X2 prime, again in weaker norm. It is easy to show that E and the first and second assumptions imply the expansion to the second order terms. This play the role of the second derivative, and And again, we have this estimate for R. Now, and finally, phi and f satisfy similar conditions. Therefore, phi and f have the following expansions. We see that here the role of second-order derivative plays by Q0, and for f, QF. And define for given Karush-Kuhn-Tucker point the quadratic functional omega, which is Q0 plus lambda hat QF plus y hat star Q. We also need the notion of the so-called critical cone. It can be defined in different ways, but we shall define it in the simplest way, like that. Here we have inequalities only for active indices. Assumption 3. There exists a constant C0 such that omega is estimated from below by the norm, weaker norm of x squared on the critical cone K. And now theorem, second order sufficient condition for the problem with two norms. Let assumptions 1, 3 be fulfilled, then the following quadratic growth condition for phi holds. There exist constant C and the neighborhood such that in this neighborhood we have this estimate for all admissible x from this neighborhood. So we have here estimate again with a weak norm squared. And hence x hat is a strict local minimizer in the problem. Now we need one more assumption, which is the same which was done in the paper by Cibulka, Kruger and Donchev. For Karush-Kuhn-Tucker point x hat, lambda hat, y star hat, we split the set of active indices E into two parts. E0 are those indexes for which lambda Lagrange multiplier is equal to 0, and E1 is the set of indices such that Lagrange multipliers are positive. Assumption 4, which is called strict Mangasarian-Faramoy's constraint qualification. The image, again, the image of G prime of x hat x is closed, and this condition, linear combination of the gradients of f prime at the point x hat plus y star G prime of x hat is equal to 0, but all multipliers are all multipliers are arbitrary except of multipliers which belongs to this set for I belonging to I0. Lambda I is non-negative, and the multipliers which belongs to I1 are arbitrary. If this holds, then lambda I is equal to 0 for all I, and y star is equal to 0. This is really stronger condition than Mangasarian-Faramoy's constraint qualification, and in particular, this condition implies that the operator G prime of x hat is surjective. And moreover, this condition implies that the triple x hat lambda hat y star hat is the unique Karush-Kuhn-Tucker point if we fix x hat. Multipliers are unique. Now we want to define the mapping. The Karush-Kuhn-Tucker system can be formulated in a more compact way as following. Lx prime is equal to 0, g of x is equal to 0, f of x belongs to the set, to this set, which is the normal cone to Rm plus at the point lambda. And obviously the condition f of x belongs to this normal cone incorporates the complementary slackness condition lambda f of x is equal to 0. Define the Karush-Kuhn-Tucker mapping f from x times Rm star. Star means that this is the space of row vectors of the dimension m times y star to Rm times y times x star. It's defined here. And the elements of image space are denoted by xi, eta, and zeta. Here we have xi, eta, and zeta. Then Karush-Kuhn-Tucker system is equivalent to condition that 0 belongs to the image of the point x lambda y star. And further we set x bis consists of all those functionals which are continuous with respect to the weaker norm prime. And we define the norm bis of the functional x star, which belongs to this space, as supremum of model x star of x. Supremum is taken over the unique ball, but the norm is weaker norm. This is a weaker norm, and since this ball is greater than the ball of, defined by basic norm, therefore we have obviously that this norm bis is greater or equal than norm basic norm in the space x in the adjoint space. Define the space x equal to x times Rm star times y star with the following two norms. The first norm is basic norm, norm x plus model lambda plus norm y star, and a weaker norm, which is the norm of x weak norm plus model lambda plus norm of white star. Also define the space z, x bis times Rm times y, with the following norm of z is equal to model xi plus norm of eta plus this norm which was defined above of zeta. Observe that due to assumption 2, we have that the gradients of fi belongs to this space, and y star g prime of x, this functional, also belongs to this space. Thus we have a mapping from x to z. And now the main theorem, the main abstract theorem, which generalizes the result obtained by Cibulka, Donchev, and Kruger. Let S hat be a Karush-Kuhn-Tucker point for problem MP, and let assumptions 2, 4, first one is not needed because 4 is stronger. Assumptions 2, 4 be fulfilled at this point. then the Karush-Kuhn-Tucker mapping F has the property SMSr2 at S hat for 0. And precisely this means the following. More precisely, there exist constants A, B, and kappa such that for every Z, Xi at zeta such that the norm of Z is less or equal than B, and for every solution S equal to X lambda Y star of the inclusion Z belongs to F of S, such that the distance between X and X hat less or equal to A, and this is only this condition define neighborhood in the space X, and this is important because we don't need that lambda is close to lambda hat and Y star is close to Y star hat. Only this condition holds. Then we have this inequality that S minus S hat in the weaker norm is less than or equal to kappa norm Z. This is the main result. So I have time. Now I would like to show you how to apply this result. We consider the Meyer problem. The time interval t0 to 1 is fixed, and it is necessary to minimize the endpoint functional, which depends both on x of t0, x of t1, subject to the following constraints. X dot is equal to f of xu. We have equality type constraints, endpoint constraints, and we have inequality type constraints, endpoint constraints. And we assume that all functions here, phi0, f, psi, and phi, are C2 mappings. Of course, this is not quite Meyer problem because we have here a control system. But from other hand, we do not have constraint of the type U belongs to U the great. So this is not, in fact, this is not optimal control problem. It's better to be qualified as the general problem of calculus of variations. And briefly, we call it Meyer problem, the Meyer problem. Okay. We consider the Meyer problem for trajectory control pairs W, X, U, with measurable and essentially bounded U and absolutely continuous X. Thus, the admissible point in the problem belongs to the space W11 times L infinity, which is denoted by W, with the norm, which is the sum of the norm. And we also consider a weaker norm. Here we have L2 norm for the control. We have also C norm for X, but it is not important. We could write also the norm of the space W11. Denote by Q the pair X of T0, X of T1. Alpha is vector of Lagrange multipliers, alpha 1, alpha k. And let us introduce the Hamiltonian or Pontryagin function. It's more correct to say, because we don't maximize it. PH, oh sorry, here we have to, I'm sorry, here we have to write PF of XU, of course. And L is the endpoint Lagrange function, combination of phi I and psi. And we have the following theorem, which is the first order necessary condition. Let xu belongs to w is a local minimizer in the Meyer problem. Then there exists a non-trivial triple of multipliers alpha 0, it's multiplier for the cost, alpha, beta, and p, such that the following conditions hold. This is well-known local minimum principle. And let w hat, x hat, u hat be an admissible point in the Meyer problem, and the tuple, this one, satisfies these conditions. Assume that alpha 0 hat is positive, and then we can set alpha 0 hat equal to 1. And also we define E0 and E1 as before. E0 is the set of multipliers such that this multipliers are 0, and E1 multipliers which are positive. The next assumption is an analog of the strict Mangasarian-Fromois condition. No, it's more or less clear how to formulate it. If we have alpha beta p with alpha I non-negative for all I belonging to E0, and this set of conditions holds. Here we have 0 for the cost. Then these conditions imply that alpha is equal to 0, beta equal to 0, and p equal to 0. All multipliers are 0. Assumption A1 implies that for a given pair, W, oh sorry, I have not a lot of time, W hat, the tuple satisfying these first order necessary conditions with alpha 0 equal to 1 is unique. We define the quadratic form by this formula, and we define the critical cone as usual, and we consider this coercitivity assumption A2. Omega is greater or equal to C0 times W prime squared, and this condition implies the quadratic growth for the cost. I would like to know that all assumptions about differentiability with respect to two norms for the problem mappings, which were made in abstract problem, are fulfilled automatically here. We define these two spaces, and we consider the perturbed system of optimality conditions. And the main result is the following. If this tuple is a solution to the original optimality system and assumptions A1, A2 fulfilled, then there exists constants such that we have such that for every z satisfying this condition and for every solution S of the perturbed system, it holds the following inequality. No, thank you very much for your attention. That's
all right. Thank you very much, Nikolai. You finished 7:29. Well timed. Does anyone have any questions?
Yes.
I don't see any hands up. So how about I'll send a clap to Nikolai. I thought it was good talk. And